In this lecture, we are covering Chapter 8, which is on Schrodinger's equation, the Born rule, and some examples of applying the Schrodinger equation. We're starting with the time-independent Schrodinger equation, which follows historically from 1925 when Erwin Schrödinger looked for a wave equation for the de Broglie hypothesis. And Schrödinger realized that using a eigenvalue method in which you separate out the time and spatial dependencies of the waveform simplifies the matter and is relevant for situations such as an electron in the hydrogen atom, where you can build up standing waves and the potential energy does not have a time component to it. It's time independent. And so we'll deal with this simpler form of the equation first. And what we can do is start with the traveling wave, but we separate out the time and the spatial components. So we have the wave function psi of x and t is equal to a, which is a constant, times the exponential of e, the imaginary number, times the wave number k, times x minus omega t. So we separate out those two components, where we get e to the minus I omega t, which is multiplied by this constant, times e to the I kx, and we call that the time-independent wave function. All right, now for this type of wave function, we have an eigenvalue equation, which we'll see you can satisfy when you put in the solutions. And here you have the second derivative with respect to the variable x of psi, and that is equal to negative of the wave number k squared times psi. All right, from here what we need to do is look at what this wave number is in terms of the de Broglie wavelength. So we have that k is 2 pi over lambda, and we know that from the de Broglie relation that this wavelength is given as h over p, where h is Planck's constant and p is the momentum. Okay? So what we can do is substitute that in, and we get so we square that, so that's 2 pi over h squared times p squared times psi. All right, now what we can do is also use the reduced Planck constant. H bar is h over 2 pi. Bring that to the left-hand side. So we can bring over the negative h bar squared, and then we have second derivative. And what we notice is that we have p squared over here. And what we can use as well, because what we're interested in is putting this in terms of the total energy of a system. So we'll put total energy of the system is E is equal to the kinetic energy of that single particle plus the potential energy of the system, V, which again does not depend here on time. It only has a spatial component. So we also know that the kinetic energy, K, for this non-relativistic particle, remember Schrodinger's equation is only valid for non-relativistic particles, is the momentum p squared over 2m. So if we return to this equation, and we notice that if we divide the p squared by 2m, you get the kinetic energy. So we have to do that on both sides of the equation. And we can now substitute that. That is equal to the kinetic energy, which is equal to E minus V. All right, so finally writing this out, we have minus h bar squared over 2m times the second derivative of psi with respect to x. That's a d dx squared. And that's equal to then this e minus v of x multiplied by psi. All right, so what we do then is we look for standing wave solutions. An example is shown in the lower right.